Wonderful words of life, offer pardon and peace to all. Wonderful words of love. Jesus, only Savior, sanctified forever. Beautiful words, wonderful words, wonderful words of life. Beautiful words, wonderful words, wonderful words of life. Amen.
Amen.
We're confident that there are more going to be joining us here in a few more moments, but we're going to go ahead and get started. We promised that we'd start right at 4 o'clock. And so we've sang some songs. We want to just bow our heads and pray together as we begin. Gracious God, we thank you today for your blessing in our lives, your presence, your spirit, and ultimately your power that's been displayed throughout the universe to create all things. And today on this creation day, where the world around in North America is celebrating creation, we just want to reflect and thank you for being such a good God. And now as we engage in this seminar this afternoon by Dr. Stephen Schiller, we pray that you would lead, guide, and direct. May your spirit come and fill our hearts, give us wisdom, insight, and understanding so that we could learn and grow. In Jesus' name we pray. Amen. Amen. All right, Dr. Schiller, we thank you for coming back and sharing with us today. And at this time, the time is all yours.
Great. I got I'm mic'd up. Can we turn these two lights off? Yes. There? I saw them go off once. I thought that would be great. Well, good afternoon. It's wonderful to be here again and be able to share some things. There's a lot of things that are, going on in the world, and especially in the scientific community, where there's a lot of effort being put out to try to understand the universe and how our solar system works, and really the desire to find life in other worlds, find other worlds and then find life on them. That's motivated a lot by evolutionary thought that life can actually turn up anywhere if you can get the right conditions, and those conditions are that which worlds in which you can have liquid water, that is, they're at the right distance from their parent star, where it's just the right temperature like it is here on the Earth, and you can have a planet that has liquid water. And if you have a star providing energy and it's warm enough, and you have the materials there, like especially carbon and oxygen and those things on that world, somehow life will spring of itself and just come into existence. So there's a lot of effort to try to show that this concept is correct by putting telescopes up in space and being able to find other worlds first, other planets like our own, and then see the signature of life on that world. So what I wanted to do today is just get you familiar with some of the science that is being utilized to allow us to explore our place where what might be going on other elsewhere besides in our own solar system. And then because it won't be too long. I mean, our technology is getting so good, especially after putting the James Webb Telescope in orbit recently, and in other very sophisticated sensor systems in space. We do have the technology to be able to explore worlds once we find them, for the evidence, for the signatures of life that you can see in the light that comes from him. And I'll talk about that a little bit. Because I would not be surprised within the next 20 years that you hear the scientific community, the secular scientific community, telling us that they found a world with life on it. Because there's ways of being able to determine that. And so I'm going to say, well, don't be surprised if you hear that. Because as I was talked about this morning, the Bible tells us that God created the entire universe for life, not just us. And so if they do find evidence for life, it's just they're not going to find aliens or anything like that. They'll just find a signature of carbon-based life, much like ourselves, and what we find on this world. So let's look at some of the technology, or some of the research that has been done to do that. First of all, I wanted to say that you're able to find out how to turn those lights. I saw them go off once. They're off. They're off now. Okay, thank you. I think that'll make it easier to see what's on the screen. Yeah, the Seventh-day Adventist Church is very unique from other churches in many ways. One of these is that our theology allows for the recognition that there can be other worlds with beings on them like us that God has created. What we'll identify, though, is that it's different from the Star Wars and the Star Trek type universe that you see, in that if there is life out there, it will be one in which it's not fallen worlds like us, but worlds that praise the Lord as He would want us to, and have a situation where they live in harmony with God and His kingdom that He has set up for all of these beings to have a loving relationship with Him. So here's some comments that have been published mainly in a book called Seventh-day Adventists Believe, and it kind of outlines that's put out by the church. It kind of outlines what they do. It says, first one is, as a fundamental belief, the Seventh-day Adventist Church, the doctrine of the great controversy, and that's that's something that the Adventist Church holds as an understanding of what's going on in our history and what's driving us towards His second coming, is to resolve the great controversy. But the doctrine of the great controversy reveals the tremendous battle that touches every corner of the universe. Okay, so it is one that engulfs all that we see out there in the visible universe. Second is, an important participant are the many worlds with intelligent beings God also created, such that throughout eternity the redeemed will witness to the unfallen worlds about His Christ's matchless love. We are here dealing with a situation where we find ourselves separated from God. It's a choice of our own. That is a template for other worlds to be able to see what that kind of choice will result in. And that's a part of what the great controversy that we talk about brings about, and allows, it takes advantage of in trying to deal with the problem of sin. However, most creationists, young and old universe, it doesn't matter, use recent discoveries of science about the inhospitable environment of the physical universe and the endless characteristics found for the fine-tuning of life to claim that conditions for habitability exist nowhere else but here. So Hugh Ross is one that is, he's an old universe creationist, but he holds his position that because of the need for intelligent design and intelligent causation for this world, there's the fact that sin. He thinks many of them think that it infects the whole universe, and thus we'll have wars between worlds if they do exist, therefore. And also that if that Jesus would have to go die on all these other worlds, just like he did here, in order to bring them back. And so it's that kind of reasoning in which they will say that, well, if there is life because of the fall and the nature of how sin has affected the universe, then we're the only. This has got to be the only place where this great controversy would exist, or at least the effects of sin will exist and originate. As a denomination, the Seventh-day Adventist doctrine stands nearly alone, teaching that there are many inhabited worlds not fallen to sin, possibly millions. And that's the difference, is that if there is other worlds out there, the position is that they're unfallen. They're not fallen. We're the only ones. And that's what allows there to be a consistency between the idea that sin does only exist on this world, but there can be life on other worlds. Okay, so is the book of nature telling us a different story than the Bible? And some of these things are held out in Job and Isaiah and Revelation. What I wanted to do was to say, well, first of all, do other worlds like the Earth exist, or are there other solar systems or planetary systems like ours? That's what I thought I'd share with you some information about what the recent situation is. I can tell you right now that until the 1990s, we had no evidence there were other planets around other stars. That is, other star systems that contain planets, like Jupiter or Neptune or those, or let alone Earth-like planets. It was only when our technology, we put telescopes in space, and our technology on the research telescopes improved, and specific missions that were designed by NASA and other European space agencies that gave us the ability to put the type of instruments in space and develop the technology that allow us to identify planets. That there are really planets in other star systems. And here is kind of it's a cumulative plot of the number of planets we've identified and confirmed by multiple research efforts. And so you can see that that up until I think it was 1996 or 97, where they discovered the first one is actually a planet around what they call a neutron star, but a special type of star that's far different from our sun. So there wasn't expected to be any livable planet. But there's been many others that have been discovered since, and I'll talk about how this was done. That you can see here, this is the total number of planets around other stars that we know of, and there's over 5,000 planets that have been discovered. As of this month, this total for now. You see, and there's different methods. These just list the different methods at which they discover them, and I'll talk about a few of them. And you can see that the green one, the transits, is the most common method for finding planets because there was a specific mission in space for looking for planets, and that was very effective at identifying them as planets crossed in front of their stars from our perspective, kind of like a solar eclipse, where instead of the moon, a planet would move in front of the star. Now this here just kind of summarizes those main 4 methods, the top 4 methods of which we detect these planets around the stars. The first one here is called the radial velocity method. And this is, stars themselves emit light. They're all just, the sun is a star. And so they emit light just like our own sun. And as you can go out with a prism and break the sunlight into various colors, what they call a spectrum, that's what scientists do at the telescope. They take the light of the star, send it through a spectrum, and are able to spread the light out. And it turns out what you see in the spectrum from blue to green to yellow to red, that there's lines in it. That is, in the atmosphere of the star, as the light leaves the star, there's atoms there that remove some of the light at very specific colors, and those lines are very sharp. And so what happens is that because if there's a planet orbiting around the star, it's going to be tugging on the star, and so they both orbit around their common center of mass, just like being on a teeter-totter. The pivot is the point in which they balance, and you bounce up and down around that point. Well, stars and a planet will orbit around their common center of mass, and the star itself will actually move towards the Earth and move away from the Earth. And so what happens then is that these lines, because of what is called the Doppler shift, these lines oscillate back and forth, so that when the star is moving towards us here, and we're observing it with the telescope, the astronomers see these lines moving towards the blue colors, the blue end of the spectrum. These lines will shift back and forth, and as it moves away from us, as it comes towards the Earth, it becomes the lines shift towards the blue part of the spectrum. As it moves and rotates away from the Earth, the lines move to the red, and so they oscillate back and forth. And the time it takes for them to oscillate back and forth is going to be the period of the orbit of the star. So as they go around, you can just simply use this as a speedometer, but it also tells you what direction they're moving and how long it takes for them to move around, the planet to move around the star, and the star to move around the planet. They're the same, not going to be exactly the same, because they're moving around the center of mass. So this is the radial velocity method, and this was the early method that was used to detect planets around the stars. They watch these things move back and forth, and it turns out by Kepler's laws of gravity, you can figure out what the mass of the planet is relative to the star, also by how large the oscillation is. Not just the period. Once you know the period and the magnitude of the oscillation, you can get the masses of and so we can know how many Earth masses the planet is, how big it is compared to the Earth. And the next method is this one here called the transit method. And what happens is, if you point a telescope at the star and the orbit of the star is lined up, it actually the star will be seen from the Earth as passing right across the star. Well, the planet doesn't emit light like a star does, like the sun does. We don't emit light like it does. And in fact, if we're looking at from this, it's going to be dark on its side. And so what happens is that you measure the brightness of the star very accurately, and it's going to be constant, nearly constant. And what happens is when the planet moves across the star, the star becomes dimmer because it's blocking pieces of the star and the light that gets to it, so it appears fainter. And so we can time the length of this eclipse know the depth of it. We can get from the depth and the time it takes for the eclipse to occur, we can get, again, the orbital period and some information about the size of the star. So this transit method, so as a planet transits across the star, it can be detected. And then knowing this from the properties of the star itself, we can get the relative size of the planet relative to the star. So that by the depth of the eclipse, because if it's a bigger star, it's going to block out more. Bigger planet, it's going to block out more light. If it's a small, teeny tiny planet, it's going to just block out a very little bit of light. So we can actually identify the size of the stars that way. And then another way is just direct imaging. There's techniques where we can actually block the light of the star. This is a star here that would be blinding everything in the camera so that you couldn't see these planets, but we can actually block the light of the star within the telescope, or there's techniques for doing it digitally as well, and actually see the planets that may be orbiting around it. So this star system here has 3 planets around it, and by subtracting out or removing the light of the star itself, the planets which are far enough away from that star, we can actually see them directly and look at the light from those planets directly as well. And then there's this weird process called gravitational lensing. This is really a neat one because it's based on Einstein's theory of relativity, where when light passes around a star like our sun, from a star, the gravitational field causes the light to bend, the path to change. And so what happens if you've got a telescope here looking at a star, it has a certain brightness. When the planet moves in front of as the planet around a star, it'll actually pass between the Earth and a more distant star. So this is a star that we're looking for planets around, and as it moves along that, interrupts that line of sight, the gravity bends the light and causes the brightness of the system, the planet-star system, to get brighter, and it focuses the light just like a lens does. If you take a light and a lens, and take the light of the sun and focus it, you can light a piece of paper on fire, because you're concentrating the light, and because it's making that spot get brighter. Well, this is doing the same kind of thing. And so when the planet first moves in that position, there's a spike, and then when the star moves in that, as it continues to move on, as it's moving from left to right here, or right to left here, the planet. The star that's being observed by and this background star gets brighter, and so you get a spike here when the star gets through. And so this spike here before the next spike in the brightness gives us evidence that there's a planet there, because it should just be one spike if that occurs, just so the single star moving in front past a more distant background star. And so the bending of the light from the foreground star and the planet gives it away. Okay, so these are the main processes that have been used to find planets around other stars. And so this here is a plot that shows what kind of planets we've been finding. And there's all different, in our solar system, we've got 8 different planets. Mercury's the closest, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. They're all different sizes and different properties. Our Earth is this size here. And it's a rocky planet. It's very dense, and its mass is higher than this is Uranus here, and this is the size of our planet Pluto, Jupiter, I mean. And you can see that 11 Earths can fit across Jupiter, so it's big. This is the great red spot on Jupiter, and it's an atmospheric storm that's been observed there for hundreds of years. And ever since the first telescope was built, and so these points here plot most of those 5,000 planets that have been observed and tell you where the orbital period is. Remember, our Earth has a period of about 365 days, and so it would be over here. That's about the distance of the Earth. These are planets that would be at the distance of the Earth from the star, and these would be much closer. And this is the relative size in the y-axis here. And so you can see all these up here are Jupiter-like planets have been discovered. These are Uranus and what they call super-Earths type planets. And then there's rocky planets that would be more like the Earth, but are some are smaller than the Earth, but most of them are bigger. And over here, these are going to be planets that are very close to the star. So they get hot Jupiters up here, lava worlds like our Earth. Because they're so close, it'd be too hot for these. Won't have life on them. These out here are planets that are just harder to detect. The closer the planet is to the star, the easier to detect. So that's why there's so many of these that are found to be closer to the planet to the star than the Earth. So we're of these about 5,000 stars. You can see how they're distributed in terms of Earth-sized planets to Jupiter-sized planets. And these are the easiest ones to detect out here. That's why you see them farther away from the planet. Because their mass is higher, they're large, have more mass, and their ability to be detected by the methods that I showed are more effective. So the goal here in the research was to identify, well, how many Earth-like planets can exist in our galaxy and in the universe? So there was actually a research study known as the Kepler mission, where a telescope was put into space to detect planets that passed in front of their star. This is using the transit method. That is, when a planet moved in front of the star, the telescope would measure the entire light of the star and see if it dipped a little bit, if it became fainter as the planet went across. And so that's what that was a technique that was used, and it was one in which they surveyed a piece of the sky for over 3.5 years. Turned out to be 4.5 years. It was originally a mission for 3.5 years, but it got extended a little longer, in which they were able to watch a bunch of stars and see if there was these periodic dippings in their brightness as a result of a planet passing in front of it. And so what this telescope did, it had a bunch of cameras on it. Camera's not much different than what's found in your cell phone. And they had a bunch of them here, and so this is the image from the focal plane of the telescope, and this is the camera image that it would show, and it observed a very wide field of the sky, and this is where these camera sensors, the cameras themselves, pointed was near Cygnus the Swan up here next to the Milky Way, and it stared just at that location for 3.5 years. And And so what we saw then is that there were, over 170,000 stars that were imaged, and you can see them dotted across these different focal planes and the camera detectors, and showing some bright ones, but a lot of them were, all very much this, close to the same distance away in this direction. And they just stared there. Every minute they would take a snapshot in that direction of the sky, and they did this for 3.5 or 4.5 years. And so they would measure the brightness every minute and did it for that length of time, and they looked to see how many times a star would decrease in brightness, if they could see any at all. And it turns out it was very effective. They did a very good, a careful job about making these cameras very sensitive to light changes, and were able to detect many, many planets. And so here's some of the planets they detected in some of the measurements. I mentioned that when there's a small planet, it makes just a very little dip. When there's a big planet, a bigger planet, it makes a deeper dip, and depends on where it crosses the disk of the star. You can see that these periods are only very short. They're only a few days. It only took a few days to go around the star. It means they were very close. And these worlds are going to be, these are the easiest to detect. So, and the size of them in terms of Earth's were 4 times to 18 times the size of the Earth. Turned out to be determined by by how large the disk was of the planet compared to the size of the star. So, so what did they find in terms of planetary systems? They found many that had multiple planets like our own. We've got 8 planets in our solar system, and they found they have found planetary systems that were very similar to ours, and ones that had multiple planets, even almost as many as we have in our solar system. You can see here, this blue circles is a planetary system called Kepler-11, and so it's star identified as star number 11, observed by the Kepler telescope. And you can see by the orbits here, there are 6 planets that were found around this star, and the star is very similar to our sun. And but it turns out that these planets are their orbits are smaller than the orbit of Venus. Venus is a very hot planet because it's close to the sun. The planet needs to be, if the star is like our own sun, it needs to be out to close to the distance of the Earth before it's one in which that will be habitable. But this one, they found these 6 planets in which all of the 6 ones existed closer to the star than Venus. And so they're going to be way too hot for life as we know it to exist. But what we've done is detect a planetary system that we can, different from ours, a completely new planetary system, and be able to see, well, is its properties the same, even though the same as our planetary system, as our solar system in any way? Well, it turns out that this system here, the orbits are very circular and very lined up in a flat plane. They're all within 1 degree of having a different tilt relative to their to the plane of orbit for all the stars. And so this turns out to be a very stable system. It has the ability to exist for long periods of time. They don't get disrupted. They don't interact. They don't bounce into each other. They're very calm in their existence and just continually orbiting and orbiting around each other. And so been able to follow this planetary system for quite a number of years, about 10 years now, for their different methods, and they detect the same thing. Just a system in which is very stable, much like our own solar system. And this is incredible information that confirms the idea that planets can exist around other stars, that do exist around other stars, in a geometry and orbital kinematics that is very similar and stable like our own solar system. Actually, if you let this thing continue to go, this planetary system, it could last for billions of years without much change. And so it is a very stable system with for this system, for these stars. You know, there certainly may be planets farther away that it's in away, on Earth-like distance. We just haven't been able to detect them yet. So there's more to come in this kind of research. And this here just depicts what kind of planetary systems. There are many systems that have been discovered in which you have multiple planets, from Earth-sized to Jupiter-sized planets in these planetary systems. Here's our own solar system. Here's the Earth. Here's Jupiter out here. And you can see where the planets fall on these various different stellar systems that have been identified by Kepler and other missions, other studies, such as using the radial velocity method to identify the positions of these planets. And you can see some are have big planets close to the star, bigger than our Jupiter. Some are a lot of smaller planets than Jupiter, but there certainly are planetary systems out there that we know for sure are in many ways look a lot like our own solar system. So, what does this tell us about understanding how many planetary systems like ours exist in our Milky Way galaxy? Well, the Kepler mission, as you can see, here's our sun, and this is a picture of our Milky Way as we know it from measuring and plotting the positions of stars and clouds of dust and gas that exist. And when, as I mentioned, the Kepler mission looked at a specific star field and stared at it for years. And it turns out it was in this direction. So what it did, it allows us to get a statistical evaluation of the population of planetary systems in the Milky Way. And so as we sample this location, in this cone here that was viewed by the telescope, this gives us a volume of the Milky Way that we know how many planets there are, and so we can use that to estimate how many planets there are in the rest of the galaxy. And we watch stars out to 3,000 light years away. That is, they're far enough. Some of them are far enough away. It takes 3,000 years for light to get to us from them. But that turns out to give us a distance that we're observing the stars. And so they extend here from the sun out to about 3,000 light years in this cone. And we're able to sample the number of stars there and how many planets per star that existed in this volume of this cone. And then we can use that to estimate how many there are in the habitable zone of our Milky Way galaxy for the entire galaxy. And in terms of this sample, this is what we found out, is that of all the planets, of the planets that the Kepler mission discovered, which was 2,600 different planets, almost 16% of them were Earth-like planets. 20% were super-Earths, or planets that were bigger than the Earth, but smaller than Uranus or Neptune. There were 20% of the planets were for Neptune-like planets, large Neptunes, out to Jupiter-sized planets or larger. They discovered greater than 6% of them were. that were found in this sample. But there are a lot of Earth-like planets. Almost, over 16% of the planets that were found were Earth-sized planets. I shouldn't say Earth-like planets. They're just simply Earth-sized planets. That's all they could tell us. And they, of course, varied at different distances from their star, and thus their habitability was still uncertain. Okay, so the question was, well, how many of these Earth-like planets exist in our Milky Way? Well, Kepler detects only planets that with the orbital planes that are aligned with the direction of the Earth. So there has to be a certain alignment, and so there's a sampling bias. And so they have to correct for that. And assuming exoplanet systems have random orbital inclinations, some of them will produce a transit, some of them won't. But we're just seeing ones that do produce transit. They don't have to do a transit to have a planet around a star. They could be just aligned, their orbits could be aligned so they didn't pass in front of the star. But we could correct for that, assuming that random orbital inclination exists. And so assuming there's 200 billion stars in our galaxy, in the Milky Way galaxy, that exist in the galactic habitable zone, where planets would most likely exist in favorable environments, 2.7% of the hosts are called Earth analogs, that is, Earth-sized planets in the stellar habitable zone, orbiting the sun-like stars. That would be planets that were at the right distance from the star, that liquid water could exist and life could exist there. And what we find out is that many of them were multiple planets in the system. Based upon these kind of estimates, the scientific community has identified that on the order of 2 million planetary systems in our Milky Way galaxy alone that have one or more planets and have just the right conditions for habitability down to the solar system scale. So that's 2.5 million potential Earth-like planets that are determined by this statistical survey that was done with the Kepler mission. So it's a reasonable estimate, and it's a one in which it was determined by actual measurement. So based upon here we have a Milky Way that's the right type of galaxy that's good for life. It's the location of these stars is in a galactic habitable zone, and most of them are just have a sun-like star in this estimate. Each is a multiple system required for habitability. That is, Jupiters and Neptunes need to be part of it, and so that appears to be that's part of the assumptions, is that they also have to have large planets that actually protect our Earth from collisions and also help with the stability of the planetary system. They have just the right type of orbits, circular orbits and coplanar. The orbits are all lined up in the same plane, and the planet with the right distance from the host star, so that the planet themselves is in the stellar habitable zone for that star system. All those are, these characteristics are part of this 2 million planetary system estimate for our Milky Way. This is fascinating. This is observational evidence that other planets do exist. There's the potential for lots of planets in our just in our Milky Way to have the ability conditions much like the Earth. Though we haven't identified one in particular that is really like the Earth, there are many planets with these kind of conditions down to the planetary scale, or the solar system scale, that indicates that they have the potential to be a planet in which life like ours could live on. And so there's a lot of optimism out there that there will be found a planet with life on it, and that we will someday be, so it encourages them to look for them, for life on other worlds, because there's worlds out there where conditions appear to be right. And I wouldn't be surprised if in the next 20 years that there'll be an announcement that they've discovered life on other worlds. And so I think I mentioned that, and that's what's going to happen. So, this is 2 million planets just in our Milky Way. And remember I mentioned earlier this morning that there's a lot of galaxies out there like our Milky Way. There's billions of them. So if you've got billions of planets in one galaxy, and there's billions of galaxies, that's trillions of potential in the universe. And this is a deep field image. Oops. This is a deep field image that shows most of these are not stars, they're almost all galaxies, just in this small head of a pin-like area in the sky. And so there are lots of galaxies out there like our own, and that satisfy the conditions for being a galaxy that can be habitable with worlds in it that are habitable. That kind of gives an idea of where the research is at. A lot of progress has been made, and you're going to hear a lot of talk about the search for life on other worlds that are spurred on by these kind of discoveries. And some of the research continues. As I mentioned before, the Webb Space Telescope was recently launched. In fact, it was just December of last year, about 7, 8 months ago. And this is an actual model of the Webb Space Telescope. And it's a scaled model. So you can see, here's a person standing here. You can see how big it is. And it's got all these mirrors on it. These are the mirrors that reflect light off that point in a given they point the telescope in a given direction. All these mirrors concentrate light onto the secondary mirror, and it bounces back here to where all the cameras are and the spectrometers that are used to study the objects that are in the field of view of the telescope. These here are shields that protect the telescope from the sun. They're always lined up so the sun is down below here. And so the sunlight does not reach the telescope and interfere with light that could blind out our view of these distant stars and galaxies. And so this is kind of how it works. But you can see how big they had to pack it up into a small space as best they could, and then it took months for them to unfold it carefully and make sure it folded out to produce this. And you can see the mirrors here in the yellow that are the ones that are covered there, but that's the same thing that happens here. What the Webb Space Telescope is able to do is look for planets directly. And as I mentioned before, if you want to observe a bright planet, you'll never be able to see a bright star. You observe a bright star looking for planets around it, you'll never be able to see the planets themselves because they're so bright. So here you have, if you're able to see a planet that's fairly far away, if there's a planet fairly far away, here's a picture of a large image of the star. The star doesn't look like this. This is light that gets scattered by the optical system in the telescope. But you can see a point here, and that's a planet around that star, or else a really cool or a hot Jupiter or something like that. That's a fairly large Jupiter-sized planet away from this star that you can see here. But if there's planets closer to it, where most of them would be, you won't be able to see it unless you can somehow block the starlight out. And there's ways to doing that, and so that's what they do here. And here's that same star, potential other planets there, but it's still uncertain. But this is a technique that the Webb telescope is able to use. It blocks the light of the star. And so here's one of the first images from the Webb Space Telescope that came out recently looking for these planets, where they have blocked the light of this central star, and you're able to see light being gathered by the telescope at different wavelengths. This is in the blue part of the spectrum, the green part, yellow, and in the infrared, where you can see this planet around a star in which the light has been blocked out by optical techniques within the star. And so this exoplanet is located about 355 light years away from the Earth and was discovered in 2017. What's going to be happening in the next few years is that there's a technique that for removing the starlight in a way that allows them to look for planets closer to the star and actually image them. And it's called using a star shade, and this is developed by NASA. And a star shade is just a disk like this here, and this is a mechanical one that has been tested by NASA, in which it unfolds from a more compact position. But again, when you launch things into space, you want to keep them compact to get them up there, and then they unfold. And the purpose is to put something that blocks the starlight from the star itself that is so bright. And this is a disk, an object that's placed in front between the telescope and the star, almost 20 to 50,000 kilometers away. So it's on its own satellite. It's a separate satellite that they'll have to move, a small sat, that they'll move ever so gingerly in a position between the telescope, the James Webb Space Telescope, and the star. But at that distance, it becomes so small that it's not much bigger than the star itself. The star is so far away that it's just a pinpoint of light, and it creates a disk here that blocks the starlight out apart from the telescope itself, so the light doesn't actually enter the telescope, and they don't have to worry about trying to keep the light from being scattered within the telescope and interfere with its observations. But it allows you to block the light, and they'll be able to see individual planets. So this is something that's coming down the road in the next 5 to 10 years, a technique that will be used for the James Webb Space Telescope and other space telescopes that are online to being launched here in that time period as well. So you'll be seeing more of that. So this is just a technique that is under test right now, and they're developing a small sat that can deploy this kind of what they call a star shade. But it involves aligning two different satellites so that they're perfectly in line between line from the telescope to the star shade to the star. And that's a very tricky thing to do, but it is possible. But with the Webb Space Telescope, as I mentioned, it showed here, it's actually able to see the light coming directly from the star, from the planet, and it observed a transit of a planet across the star. And what happens is that the light from the star goes through the atmosphere of the planet towards the Earth and towards the telescope, and it collects it. And so the atmosphere appears, the effects of the atmosphere appears in the light that comes from the star. And so as it passes in front of it, the atmosphere of the planet itself absorbs light, as light from the star passes through it and continues on towards us here on the Earth. And because when they look at that star, they'll see if they can look at the star when the planet is not in front of the star and when it is in front of the star. And they measure the brightness at 2 different times. And they can look at the difference in them, how the planet affects the appearance of the light from the star in terms of its spectrum. And this is an observation that shows the spectrum of one of these planets transiting across its star that blocks light at specific wavelengths. You can't read it here. I was hoping it would be a little clearer. But this here are features that show the presence of water vapor in that planet. So here, is there really water on one of these planets? And this indicates that there is. There's 4 different wavelength features. See, if this is our Earth, the light that comes from the sun on our Earth, and the red light in a red area, the yellow represents the light from the sun, and the red area shows the light that reaches the surface of the Earth. And this is the light, and the yellow is the light that reaches the top of the Earth. As the light goes through the atmosphere of the Earth, if there's water vapor in our Earth, it absorbs light at certain wavelengths. And there's 4 different strong wavelengths at which water gets absorbed. H2O gets absorbed in our atmosphere of the Earth. Well, we see that absorption here, 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 and here on this planet that the Webb Space Telescope observed. So there's a perfect match there, and it shows that on this planet, water exists in the atmosphere. And so that's the first step to finding one of these watery worlds which life on Earth or life on that planet needs if it's there to exist. It doesn't prove there's life there. What they have to do is start looking for other features like ozone, and they can see water here because they're very strong. It's a very strong feature. But there's going to be other things like oxygen. If there's oxygen in the planet, that's a good indicator of like on our Earth, of life here. Of course, we need oxygen to live in a carbon-based life. CO2 features are here, and there's ozone features that will be strong as we get better at doing this kind of spectroscopy. We'll be able to start looking for those features, and if they find those and they find the right combination that is unique to the existence of life, then they'll say that they found life on other worlds, because they wouldn't, those features in the atmosphere of that planet wouldn't be there unless there was life on that planet. And so that's where we're going to go, and that's the kind of announcement you'll hear when astronomers say that they've discovered life on another world. They will not have imaged cities or aliens on those planets. They're looking for the signature in the atmospheric spectrum of those planets of the presence of life that could only be there if life existed. And that's kind of where it's going. And one other thing that I wanted to mention, that we have been actually visited by objects from other planetary systems. This is there was an object that came by, and this is the first one, what we call an interstellar interloper. It's an asteroid-like object. I mean, it's an asteroid, but it came from another stellar system, not our Earth. It didn't originate in our Earth's planetary system. It came from somewhere else. And we know that because here's the orbits of Jupiter, Saturn, Uranus, and Neptune, and and again, this is not, I have to blow this up next time. Very clear, but this is the orbit that it followed, and it's coming in too fast. It's not bound to our solar system because it's moving too fast. It came through at a very high speed. It's an object that was about 300 meters across, and it flew into our solar system and was only here for a few weeks as it passed through. And you can see this is a normal orbit of a comet. A comet is something that's bound to our sun. It doesn't move fast enough to escape from the gravity of the sun. But this one called Oumuamua, that was the name of it, was an object that was discovered in 2017 and approached our planetary system, passed by the Earth, and we were able to observe it with our telescopes. And it came in, zip it in very fast, went around the sun very closely, and then back out and is leaving the solar system again. So we have observed for certain objects from other stellar systems, because this could not have been originated in our own solar system. And there's a lot of interesting things going on. Our ability of being able to observe things in the world, in our solar system, has increased greatly. And so we're starting to detect objects like this that don't belong here. We find them as something that come from other stellar systems besides ours. And there's been a couple others since then that have been observed as well. So, so I hope this gives you a little bit of feel for what is, what kind of science advances there are in the study of our solar system and planetary systems. We've discovered, as I said, many worlds now, besides our own, some in very similar conditions in terms of a planetary system, not whether the world is conducive to life, that world is conducive to life, but at least on a planetary scale, on a stellar system scale, the conditions are very similar for some of these that are Earth-sized and exist in habitable zones, potentially habitable zones of these other planets. And there are certainly objects that fly by our Earth that have to have come from other planetary systems, because they're just moving too fast to be a part of ours. And so I hope this was helpful. I hope it wasn't a bit too high a level that it was difficult to understand, but I tried to break it down as best I could. But I wanted you to get a feel that there's a lot going on and a lot of new discoveries that we should not be surprised when the scientific community says they found life on other worlds, because we do have the technical capability to do that. And it is for real. It's not going to be somebody's bias doing that. It's going to be based upon just good scientific observation. And because it's not something that is going to be done lightly. Because if they say there's life on other world, or they found life on a world besides their own, they're going to do it. They're going to have good reason for being able to claim that. And so, but the technology is there to be able to do that. So, just wanted to share some of that with you today.
Thank you, Doc. Does anyone have any questions?
Yeah, there's.
Doc did a very good job.
All right.
Appreciate you sharing